and computational chemistry. Well, I can speak the presentation of myself because Alex did it pretty well. So this is redundant in a way. So as Alex said, I did my PhD here, and then I moved to 2 different countries, both Stuttgart in Germany and Japan. I was in Tokyo. Okay, but now about the research lines that I want to present here today. So basically my research is placed at the interface between computational chemistry and molecular astrophysics, or I would rather say in my case astrochemistry, because I really study the chemical processes that occur in the interstellar medium. And the research line broadly defined that I carry out in my research are astrochemistry using machine learning, and in this case I will now refer to the first part of my research, that is using interatomic machine learned potentials to study physical processes on ices. Second, surface chemistry on interstellar ices. So I studied the reactivity that occur on interstellar ices at very low temperatures, both from a computational chemistry perspective and also an astrochemical modeling perspective. And these are 2 more applied maybe research lines that I have undertook in the last year. So one of them is the study of isomerism in interstellar medium, so how different isomers came to be in regions with very cold and very extreme conditions. And finally, last but not least, the research line that I carry out in collaboration with Maria that deals with how pHs, so molecules that are composed mainly of carbon and that are structured that are much higher than we would expect, or much larger than we would expect in the interstellar medium, came to be. The overarching goal of my research, I would say, is to link the very, very elemental atomistic processes that occur at very low temperatures, and not so very low from time to time, with prebiotic chemistry. So how molecules, ever-growing complexity can appear in the interstellar medium. Great. So, well, this is also a little bit redundant, but I think it's important nonetheless for the PAMS department in the institute. So as I said, I work at the crossroad between chemical kinetics, molecular physics, and astrochemistry. And for that, I use a plethora of different techniques that intersect in the different connections of the different disciplines. So for the sake of keeping this brief, I use electronic structure theories that I couple with molecular dynamics simulations. And I train different types of potentials. It depends on whether I use on-the-fly simulations or I use embedded techniques or neural network potentials. And I unveil reaction mechanisms for different molecules that occur in space. And the chemical kinetics that I carry out, I do it with microcanonical transition state theory, or RKM. I use also capture theory, instant-on theory, and so on and so forth. Let's go into the scientific context, so the contextualization of my work. So as Pablo presented before, we are very accustomed to the cosmic matter cycle, and we have different regions in space, and every region is characterized by a distinct chemistry that provides, I would say unique, but not so unique, but well, for the sake of not being also very thorough, I would say very unique fingerprint of the chemistry of the different regions in space. That helps us, of course, to understand different astrophysical properties. My research is mostly, or for the time being, this is changing right now, but I've been working mostly in dense clouds. Dense clouds are regions of space that are very cold, relatively dense, and they have a series of conditions that are conducive to chemistry. So the main reason why these molecular clouds are considered the greatest laboratories in existence is that they have a dusty envelope over here that avoids photons to fully penetrate into the cloud, and this protects the molecule for breaking apart through photodissociation processes. And this is precisely why in these kind of regions we have detected more than 300 interstellar molecules to date. And within these very huge objects, we have 2 main phases where chemistry can happen. We have the gas phase, and also we have dust grains that encompass around 1% of the total mass of these objects, with temperatures around 10 Kelvin. The most important thing of this slide is that within these regions, we have 2 different regimes for the chemistry. We have chemistry in the gas that has their rules, and also chemistry on ice, well, on dust, that this is a spoiler, it is covered by ice. And this leads to a completely different chemistry, normally. And if we could understand all the reactions that happen in the gas and on the grain, and also taking a very simplistic approach, we could solve the chemistry in these regions just by solving this rate equation, in which we have just a balance between the molecules that are destroyed, the molecules that are formed, and in two different mechanisms overall, which are bimolecular and unimolecular. This is not really important, but the objective that we have is that we want to map all the different interstellar species, simple or not, with other more complex using, normal chemical kinetics. The main problem is that to date we have around 13,000 reactions with more than 100 and 300 species in the reaction networks. They are not detected, many of them, and some of them are include the reactions on the grain and on the gas, and they are distinct in the models. But overall, we have around 1,300 species. And this is really the biggest conundrum of astrochemistry. Most of the rate coefficients and the reactions that are considered in these models are totally guessed. So they are put into the reaction networks just by chemical intuition, or even not, even without that intuition. Don't get me wrong, so these kind of models have been very, very useful in the past. So that is really something that has advanced the field, but we can do better right now. And in order to construct a chemical model that can solve this kind of chemistry, we have a series of different processes. This is a snapshot from the chemical model that we use at the University of Tokyo, now here, of course, that includes all the different types of reactions that take place that we assume takes place in the interstellar medium. You can see there the usual suspects: two-body collisions, radiative association, reactions on two-body reactions on grains, adsorption, desorption, and so on. And as I mentioned, we have two clear rules. First of all, we have reactions in the gas, exemplified in the top square or rectangle, in which this is not totally general, but in general, we have reactions that are bimolecular in the gas. So we have two-body reactions that lead to two-body products, except in the case of radiative associations. However, in the case of the ice, and because the ice normally acts as a third body, dissipating the heat of the reaction, what we have is elementary steps that can build chemical complexity. And this is something that is traditionally considered in the field. So reactions on the grain lead to more complex organic molecules, such as, for example, the prototypical formation of the simplest, or one of the simplest organic molecules, methanol. Okay, so with that in mind, let's take a look, a little bit of a detour into the historical context of what I'm saying. So I have said that the reactions on the gas usually take place in a bimolecular context, and this is what it was thought before more or less 2006, with some question marks. So before 2006, methanol, which as I said is the most important complex organic molecule, I would say, was thought to be formed via this sequence of reactions over here. Okay, so basically we would have a radiative association followed by a dissociative recombination by an electron. An electron comes to a molecule and breaks the molecule apart, giving us the neutral, that is the one that we wanted. What happened is that when experiments measured the ratio of the products of this reaction, showed that actually this reaction channel, that it was previously thought as the most important, was very, very minor. So this really collapsed our understanding of how methanol could form, and we needed to rely on, or at that time, they needed to rely on different theories to form methanol in space. Basically through grain reactions of the hydrogenation of carbon monoxide, that is one of the simplest molecules. And then, I'm sorry for the quality, this was perfect in my computer, but well. So, well, so yeah, it's more or less, one can see it, yes. So, what? Oh, okay. Well, nonetheless. So we can decompose this kind of grain chemistry into 4 elementary processes, not considering energetic processes, into the combination of accretion or the position of molecular material on the surface of ices, diffusion of how the molecular material moves around the surface, desorption of how the molecule leaves the surface, and reaction, which is when two particles collide and they overcome the activation barriers, if any, to form the new molecules. Great. So this is precisely what I have been studying in one of my postdocs, at least, trying to try to give an atomistic description of every of these elementary processes that occur on ices. Great. So, but first of all, let's consider what I meant when I talk about ices. Well, ices or dust grains in space are, in particular in dark clouds or in dense clouds that I have presented before, are made out of a refractory material, so for example silicates or carbonaceous material, and because the temperatures are very, very low and the molecules that accrete on top of this material cannot return to the gas phase, when the temperatures are low enough, an ice mantle starts to form, whose main component is water, but it also has a seasonal, or well, I would say an epoch dependence, with different components being more important in different times of the evolution of the cloud, or even farther than the cloud. For example, carbon monoxide, carbon dioxide, and methanol. And it's in these ices where the reactions takes place, at least the ones that I study. And these ices have a particularity. So instead of what we expect on Earth, that we expect the typical ordered crystalline ice, what we do have in space, actually, in most cases again, because we cannot really draw an absolute conclusion of what happens in space, because we are in space overall, after all. So they are amorphous. So we need to simulate systems that are amorphous in nature, and this implies a series of approximations in my research that I will cover. The most important thing here, of course, is that the potentials that we need to study these kind of systems need to be anisotropic. So we cannot really simply use a typical crystalline solid and calculate things on it, because it wouldn't work here. And the typical ways of overcoming this limitation is to use periodic slab, but with some amorphicity, and study them with DFT. Similarly, if the process that we want to study, the DFT, by the way, density functional theory, which is an approximation of how to solve the Schrödinger equation. Clusters and DFT, if the problem that we want to solve is very local, we can use simply a cut of an ice and study them there, or classical force fields. Both of all of these approaches have advantages and disadvantages, as the technique that I use. Of course, it also has advantages and disadvantages, and what I use for studying these physical processes are neural network potentials. Using an in-house model that we develop at the University of Stuttgart and we use at the University of Stuttgart, we create interatomic potentials able to simulate these kind of amorphous systems for the treatment of ices with thousands of atoms. This is the best we can do. And the nice thing, so the neat thing about these kind of potentials is that they can simulate the formation and destruction of chemical bonds, something that will also be important in order to study reactivity, of course. But these kind of systems, or these kind of potentials, are very expensive to generate and require to have a prior knowledge of the system. So they are not generally applicable, at least at the stage that we are now. So we need really to decipher a little bit the physics of the system, or better said, the chemistry of the system, before applying it. But we have, well, this is a quick reminder of the system, of the processes that we have simulated using machine learning potentials or neural network potentials. And we have success in applying these kind of potentials to treat the systems or the processes that I was talking about. So over the years, we have worked in simulating absorption of atoms and simple molecules on interstellar ices. We also have constructed the free energy surface of a full amorphous, or well, a cut of an amorphous surface in order to study diffusion, and we have been able to obtain diffusion constants out of it. And lastly, and here we have a recent paper also that was accepted, we have succeeded in using these kind of potentials to study reactivity and non-thermal processes that occur on the ice, such as, for example, here I show what happens when a molecule such as pH, so phosphorus and hydrogen, form and reacts and collides with the ice and have a series of energy transfer processes that lead to the desorption of the molecules. This is, by the way, the mechanisms one of the mechanisms for which we know that molecules that are formed on the gas, on the grain, can return to the gas. And with that, I have talked about the physical processes. I will be very glad to answer any questions that you have about the methodology. But since I want to cover all the different research that I have carried out in these years, I want now to talk about chemical reactivity in the gas, in the grains, and also in the gas, but I have not included so much about how I treat the gas phase. So the problematic here is that we have a pace of molecular detections in space that very, very much surpasses our attempts to understand it. So most of the molecules that have been detected recently in space, we don't know how they are formed. And this is the purpose of this line, to know how these molecules are formed. Detected or detected recently or in the past. So many of these molecules, even if they are being detected for 10 years or 15 years, do not have a clear synthetic pathway. And basically, in this research line, what we do is to construct complex chemical networks that are able to explain the formation of the different molecules. So these are simply two examples of the that we have published over the years. Here, for example, we explain an alternative way of forming methylamine, or different molecules that have this skeleton, this kind of skeleton in which we have a parent molecule that is a very simple hydrocarbon. And in order to do this, we need to simulate two different processes that occur on the ice. We have two different mechanisms mainly that contribute to the formation of these molecules. We have the traditional Langmuir-Hazelwood mechanism, that is a mechanism that occurs on surfaces where two pre-absorbed molecules move on the surface, or at least one moves on the surface and encounters a reaction partner and reacts. And also the LA radial mechanism, in which this is a bimolecular mechanism in which a molecule or an atom from the gas collides with a pre-absorbed adsorbate on the ice. And these both types of chemistry are simulated in my research. And we have another different limitation, or a different categorization of the different projects that we carry, and is in systems that we expect that do not have huge activation barriers. These are systems in which we have barrierless reaction. Every diffusion event that makes two molecules close will lead to reaction. What we study basically is the surface influence in the reaction. As you can imagine, as these surfaces are amorphous and they have, in general, water and hydrogen bond networks that form upon the adsorption of a molecule there, this really causes an effect in how these molecules react with the different agents, such as, for example, hydrogen atoms, oxygen atoms, and so on. And in systems that do not have a barrier, we can really dedicate time to take a look at how the interaction between the molecule and the surface plays a role in the outcome of the different reactions or the different barrierless channels that influence the chemistry. And in systems where we do have activation barriers or activation energies involved in the reaction, we use very simple models. Sometimes we even just fix the rotational partition function of the molecule and study with different theories how quantum tunneling affects the chemical reactivity. And here I show an example on a hydrogen abstraction. That means this hydrogen of the phosphine goes to another hydrogen and releases H2. And this reaction is, of course, mediated by tunneling, and we have calculated that over the years and include in astrochemical models. This with respect to Langmuir-Hazelwood chemistry, but as I said, I also studied LA radial chemistry, and in particular the chemistry of carbon atoms. So you can imagine a carbon atom in the gas that collides with an ice and does something. But what carbon atoms do, that they tend to be very reactive, and instead of the usual way in which we thought reactivity occurs on ices, what we showed actually is that the ices in this kind of LA radial chemistry partake in the chemical reaction, and we have proton shuttles on interstellar ices, something that we proposed in 2022, that we extended also to ices with ammonia, mixtures of water and carbon monoxide, and so on. And that led us to develop a new carbon framework in the ISM that we published in 2023, in which we can explain the formation of ever more complex molecules on the surface of ices by carbon chemisorption on different binding sites in which we have chemicals ready to react, and also we need some contribution of physisorption states on the surface. So that is something that we have done over the years as well, in collaboration with my colleagues at the University of Hokkaido. And the last part that I want to talk about the methodologies that I use is astrochemical kinetic modeling. And returning to the very beginning, astrochemical kinetic modeling is basically solve this equation for a physical conditions that are compatible with interstellar dark clouds. And now what you can see is that my research merges quantum chemical calculations with the inclusion of that quantum chemically derived magnitudes into these kind of models. I won't show many projects regarding this, just one that is probably the last one and also the most visual one, in which what we took a look at is what happens when in a chemical model we take into account the heterogeneity of the different interstellar ices. I have been saying during my presentation that interstellar ices are covered mostly by water, which is something that is true, but in some stages, carbon monoxide, that is forming the gas, lands on the ice and readily creates an apolar surface in which chemistry is different because the dipole moment of CO and water is radically different. And this in turn has an effect on the models that was not taken into account until we publish it. That is that this is the rate constant or the rate constant for Langmuir-Hiselwood mechanism depends on the times of diffusion of molecules on the surface. But this time of diffusion, in turn, depends on how the molecules bind to the surface. And this is a simple representation of what we did, but is quite loyal to reality. Because what we did is combining, again, quantum chemical calculations with astrochemical modeling. What we did is to compute the ratio between the binding of molecules on CO clusters and water clusters, finding that, as chemists probably would know without calculations, the binding energies vary in the different surface by a factor, and this is what is not trivial, by a factor more or less of 0.4. And the next step that we took is just to implement, and in the first approximation, a linear term that takes into account the coverage, the surface coverage of water and carbon monoxide, and modulates the binding energies or the affinities of the molecules with the surface accordingly. And run chemical models, many chemical models. I will just summarize them. And I will show what is the effect of varying these binding energies and including this kind of heterogeneity of the surface for a couple of, well, 4 molecules, which is acetaldehyde, dimethyl ether, ethanol, and methyl, this is acetic acid. On the right-hand side of every panel, what I show is the previous model. So the model without incorporating carbon monoxide, chemistry on carbon monoxide. And on the left-hand side panel of every one of them, what I show is what happens when we include carbon monoxide into the model. We see that there is a window of different physical conditions. Here are shown dust temperature or ice temperature and cosmic ray ionization rate, in which there is an increase, I would say a dramatic increase in the formation of complex organic molecules, which allow us in turn to propose newer scenarios for the formation of these molecules in space. Great. So now I reach the part in which I will present some new results that I have been carrying out at IFF. Basically, as I said at the very beginning, I'm very interested in the isomerism of molecules in the interstellar medium. And the molecule that is more important, I would say, one of the most important isomers, apart from HCN, that is, of course, the most important one, is formic acid. And in this work, that is close to be submitted, I would say, what we have done is to couple all the well-known chemistry of formic acid, introduce the isomeric dimension into it, and run chemical models such as the ones that I just showed. And very funnily, in comparison with the Quixote data of TMC1, that some of you may have heard of, is an astronomical survey of the Taurus molecular cloud, which is one of the richest sources in the sky for chemistry. We observed that more or less the time scale of the cloud, we observe, or using this updated chemistry, almost perfect match between the ratios of observed trans formic acid and cis formic acid. Mainly due to a mechanism that we have labeled isomerization upon desorption, in which after forming formic acid, the molecule can undergo an isomerization non-thermally after the desorption. Great. Another work that I want to highlight here is, and this is for my colleagues at the molecular astrophysics department, is we have computed the binding energies, not of molecules on carbon monoxide, but of isolated carbon monoxide on water using different models for water. What we have done is using these interatomic machine learned potentials that I've been talking about, we have created different models of ice. We have created compact ice and porous ice, and we have obtained not a single binding energy, which is something that is commonly done, but a distribution of binding energies as a function of the binding site that we obtain, that we sample. This gives rise to a Gaussian function to fit the data. And what we have done in comparison with other models is, instead of using a single binding energy that usually is the average of the binding energies, we have introduced the full distribution of binding energies into a protoplanetary disk model, finding then a new concept here, snow lines that are so regions in space where the molecules that we consider are in the gas, or are in the gas, not in the grains, where molecules dissolve. We have found that carbon monoxide is actually very spread on protoplanetary disks in comparison to what was thought before. And finally, some recent news on another research line that we have started. This is, as I said, carried out by Maria here. So what she's doing, I haven't talked a lot about how I tackle gas phase chemistry, but this concerns gas phase chemistry. And now, as you may know, we are detecting a lot of polycyclic aromatic hydrocarbon molecules in space. They are very, very complex, so they cannot be dealt with simple quantum chemical calculations, because the search for the possible chemical reaction paths is prone to errors. So what I suggested Maria is to use automated techniques to sample very, very complex potential energy surfaces, stationary points on those surfaces. And so far, I'm very happy. She has succeeded. So she has found the low energy, so the low temperature formation pathways of C5H7+, I think, yeah, C5H7+, using automatic reaction discovery techniques, in which we characterize up to 80 stationary points in the potential energy surface and obtain the corresponding rate constants. In the same for the reaction of propene with the cyano radical. So, yes, I will keep you posted on the outcomes of Maria, of course. And well, this is my summary of the talk. So I want to indicate here my philosophy for my research. So I start every project by carrying out quantum chemical calculation of some quantity that is important for the chemistry of a given astronomical region. Then with my results, I translate those derived quantities into the realm of astrochemical models. And I run the chemical models to verify if my calculations make sense in an astronomical context and adapt accordingly if needed. So yeah, thank you very much.
So thank you, Herman, for this very nice talk. So questions? Yeah.
Okay, I have several questions. The first one is, in what extent what you are using in rate constants, the result is good enough or to be quite confident with the result? Because as far as I know, I am not working on your field, okay? But always people are saying, look, rate constants is a big problem. So all the reaction mechanisms are based on reaction. So in what extent are robust what you get?
Yeah, so I will separate that question into two different, well, as always in my research, into gas phase and grain chemistry. In grain chemistry, rate constants, over the years I have come to realize that they are not that important, because what determines the chemistry is the diffusion. And the diffusion for hydrogen atom is well-defined, hydrogen atom on amorphous solid water is well-defined by experiment. So basically, even though I can calculate rate constant to a huge degree of correctness, to more or less our standards, at the end, my usual observation is that they are faster than diffusion. So basically, the determining step for the reaction is diffusion, and this is a binomial outcome. So I say, well, the reaction is competitive with diffusion or not, and that determines the outcome. So in that case, we are safe. And in the gas phase, we are completely true. So basically, the rate constants are susceptible to many uncertainties. And we do the best we can do, but we have an advantage. At low temperatures, we don't have that many channels open, so channels for the reaction. So we normally fail, if we fail, in the exact value of the quantitative rate constant. But we don't have this qualitative failure in which we, for example, miss an entire reaction channel. This is normally not the case. So we do have some errors, of course, that is 1 order of magnitude even. So that is the extent of our calculations. But we don't have qualitative errors, at least in my view.
So the second question is exactly related to diffusion, okay? Look, diffusion by itself is a real challenge, okay? Apparently, you are dealing with diffusion in a very, let's say, general framework.
Definitely.
So my question are two. Well, are you using instanton theory for diffusion?
No.
No.
No, because the hydrogen atom, which is the most important one, is deemed to be, it is deemed to diffuse thermally at the conditions.
Yeah, but the point is you have tunneling. You can have tunneling.
Yeah, for
First. And second, when you are using amorphous surface,
Yeah.
okay? I don't know if you are familiar, but if you are using scattering or diffusion theory, whatever you want to call it, there are different ways to take into account the amorphous system or surface you are using in order to get better diffusion constants.
Totally.
Are you working on that?
Not exactly in the problematic, but we do, we average over a huge number of different surfaces, and we expect that that we don't have a systematic error. So we have that into account in that way. But of course, yeah, I know that diffusion is, in my view, from the projects that I work on, the most difficult one I have done.
And finally, diffusion, you have to think in terms of physisorption, not chemisorption.
Yeah.
So how you mix it?
Chemisorption, we consider that it doesn't diffuse. So
Exactly.
We
So
don't
this is the point.
consider any diffusion.
So diffusion is the most important step when you are dealing with ice or dust.
Well, depends on the mechanism. For the Langmuir-Hirsel mechanism, yes, definitely. Yes. I would say the only.
So,
Well, quantum tunneling plays a role in some reactions, but they are not that many, and it's a little bit uncertain because I have worked in quantum tunneling a lot just to find out that diffusion is more important.
but I am tunneling on surfaces, not
On
tunneling
surfaces,
on gas
on
cells,
surfaces.
okay?
Yeah, but
Because you have to use, for example, Lindblad equation. You have to use,
Yeah.
okay?
yeah, on surfaces.
Okay.
Okay, there.
Okay.
More question? Yeah.
Just a curiosity, perhaps I missed what you say, is that the complex organic molecules or some complex molecules you obtain a larger yield of them when you consider CO grains.
Yes.
Why?
Because diffusion is very much enhanced. And this is a parametric implementation of diffusion in the model. So it's basically just a formula. It's not like we study diffusion itself. There, we just assume it takes place via the usual formulas. And what happens is that the carbon monoxide dipole moment is very low. So the binding of molecules to carbon monoxide is very low. And this has a consequence in diffusion. You can imagine it as gliding over concrete or gliding over an ice. So really the molecule can glide much more, will have much more reactive encounters and forms complex organic molecules.
Yeah.
So these temperature distributions in the binding energies is something that you apply only to CO and water, or also for the atoms? And second, I mean, you predict something that is apparently different to what other models predict. Did you benchmark this with observation? I mean, is this explaining observation better, or?
You mean for the CO snow lines? This is the next step, of course, to use observations to try to constrain whether our snow lines are correct. This is something that we have now considering, of course. Yeah, the problem with obtaining binding energy distributions is for every distribution you need to train a potential, and this is very time consuming. So far now we are focusing on the simple molecules. So what we have treated is H2, nitrogen atom, CO, and we are going now for HCO. But really, every project takes a lot of time. So eventually we will go to complex organic molecules for these distributions, but this is sadly not the case now.
This, water is like the even more important than CO.
Yeah, water is already published.
Okay.
But water is already done, not by us.
A quick question. Are you using AI?
Well, you can call it, yes. No, not really. I wouldn't say AI. It's just linear regression, a fancy linear regression. But yes,
Okay.
you can call it. Yeah.
Okay, more questions? Well, if not, let's thank Herman again. ¿Tenías? Ah. Okay, so our first speaker of the day it will be Carlos Sanchez Munoz. So he did his PhD in Universidad Autónoma in the Department of Condensed Matter, and he earned his degree in 2016. After his PhD, he went as a postdoctoral researcher in the RIKEN in Japan, where in the group of Franco Nori. This was in 2017. Then he went to Oxford University in the group of Dieter Jacks. I don't know if I pronounce this correctly, but and then he turned back to Spain in the IFIMAC in the Autónoma under Caixa Fellowship before he integrated the Instituto de Física Fundamental at the end of 2023. And now, well,
okay. Hello. Okay, thank you, Alex, for the introduction, and thanks all of you for being here and staying until the end. So in this talk, I'm going to try to give you a flavor of the type of research that I've been doing over the last years and that I plan to do in this institute. I think I tried to make a very informal talk, so I apologize if you find it maybe too superficial, but I tried to keep it entertaining. And I skipped any biography because I knew that Alex would introduce me. So I wanted to start right away with a picture that I believe illustrates the overall theme of my research. So this picture is showing a process that starts with some type of source of quantum light. And this quantum light flows into a detection scheme, and maybe before that can be used to excite matter, okay? So that the light from this system scattered from all the system goes into the detector. And then we have some detection scheme in which we can make some transformations and basically choose what type of measurements do we do on this light, and also an analysis process, okay, of now using this quantum data to infer some information. So I am speaking a lot about, and I'm going to speak a lot about quantum light. So first of all, I want to establish what I mean by that. So I'm a theoretical quantum optician. So when I think about electromagnetic field, I think in particular a single mode of the electromagnetic field, I basically think of a quantum harmonic oscillator. And there, you can describe the state of your field in phase space, as we do with harmonic oscillators. And a classical state in phase space would be just a point, right? So when you actually look at quantum states, the most classical state there is the coherent state. Okay, so this is, instead of a point, it's a blob with the minimal area that we need to have to fulfill Heisenberg's uncertainty principle. So this would be a classical state, the most classical state there is, a coherent state. So what are quantum states, non-classical states? A very famous example, for instance, are CAT states. So these are superpositions, macroscopic superpositions of different coherent states, which in phase space, if you represent the state, for instance, with a Wigner function, this coherent superposition manifests with this interference pattern. Another type of non-classical state are squeeze states, in which we take this coherent state and squeeze the fluctuations in one direction in phase space at the price of increasing fluctuations in the other direction. So as we will see, this has strong consequences and applications to do sensing and metrology. We can also have, for instance, sub-Poissonian fluctuations in photon number. A coherent state has a Poissonian photon number distribution. So sub-Poissonian states are also examples of non-classical or quantum states. And what do you need to generate all this? Basically, in most cases, you will need a cavity. That means something to store the single mode of the electromagnetic field, and some type of nonlinearity, like some atomic media. And that brings us to the paradigm of cavity QED, in which you study the combination of these two elements, which is basically my field of research. So now I want to motivate a little bit why I am interested in this process, in all this stuff. And I want to motivate it. There are, of course, many applications for quantum technologies, but I want to focus on photonic quantum metrology. And here I am using the word metrology as an umbrella term in a very broad sense. And basically, here I have many examples of what I mean by that I would put under the umbrella term of metrology. I don't know if you can see, but here I have examples like interferometry, spectroscopy, imaging, and so on. And I will go through some examples to show you how in this process different combinations of taking into account the classical or the quantum character of light at different stages of this process can lead to different applications. So the first one, for instance, in interferometry would be just to consider that we have some quantum light arriving into our measurement scheme, and we make some transformations as we can do, for instance, in a Michelson interferometer. So there are many examples of using quantum light to get an advantage, and the most famous ones are using squeeze states in these Michelson interferometers, as has been demonstrated for the detection of gravitational waves in LIGO with improved signal-to-noise ratio. And there are also examples of feeding into these interferometers entangled states, for instance, entangled in a photon number. Another application could be in this scheme, considering that we excite with quantum light matter, and we analyze the classical properties of the light emitted, and this can also have an advantage, for instance, in spectroscopy. One important example is in Raman spectroscopy, in which in this quite recent paper they demonstrated that exciting the system with sub-Poissonian light gave to a better signal-to-noise ratio, and very importantly, this couldn't be compensated by using classical light with a higher intensity, because they were already operating at the highest possible intensity before burning the sample. So this is really an absolute quantum advantage in measuring a property using quantum light. And finally, I want to show an example of imaging. Here I change the order. I'm shining classical light into matter, but I'm analyzing the quantum aspect of the light emitted. You do this by doing measurements, for instance, of correlations, which is basically coincidences between different detectors. And in these examples in quantum imaging, this is fluorescent microscopy. They are inserting fluorophores into tissues, and basically you want to make an image of the fluorophores. And they show that because these fluorophores are emitting single photons, so photons one by one, this has properties in the coincidences, and you can exploit these quantum correlations to get images with much better contrast and much better resolution. And now the experimental setups that we have are really amazing. Even this one is already outdated, because they can have massively multiplexed signals going to arrays of single photon detectors that right now I've seen papers of 500 times 500. So it's really amazing the type of correlation measurements that you can do. Okay, so from the theoretical point of view, all this process, all this stuff lies at the intersection of different fields. One would be, for instance, quantum metrology in continuous monitoring setups, because you have systems that are radiating continuously and you want to infer information from there. This, of course, connects, because we have losses and driving, to the theory of open quantum systems, and because we are studying light-matter interaction to generate quantum light, this connects to quantum optics and cavity QED. So these are the fields in which I mainly work. Okay, so I try to give you a motivation on why I am interested in this overall process. And my research has several lines that focus on different parts of this process, having the overall thing in mind all the time. And in this talk, I will focus on 3 lines of research. The first 2 focus on this first part of generating quantum light in cavity QED. I'm going to be talking about squeeze lasers and about implementing quantum optics in the terahertz. And then I will move to the last part of detection and analysis of quantum light, and I will speak a bit about how we can use machine learning to boost quantum parameter estimation. Okay, so let me start with the first topic, which is squeeze lasers. And to do that, I would like to briefly describe theoretically how I understand a laser and squeeze states. So first of all, photons in a laser beam are completely uncorrelated. That means if you detect a single photon from your laser beam, you gain no information whatsoever on what's the probability of detecting a second photon just afterwards. This comes from the theory of quantum optical coherence that established the field of quantum optics and gave Roy Glover a Nobel Prize. Then, as you all know, a laser is extremely monochromatic light. It has a well-defined frequency, and that means that it has very long coherence time, classical coherence. And if you want to visualize it as a state, that would be a coherent state, as I showed you before, which can be understood as a displaced vacuum in phase space. On the other side, we have squeeze states. So photons in squeeze states are correlated. That means that if you detect a photon from a squeeze state, you change the state and you gain information about the probability of detecting a second photon. So this type of expectation value of products of operators you cannot factorize as you can in the laser. And then they have these modified quadrature fluctuations, as I said before. And the most general squeeze state can be understood as a displaced squeeze vacuum. We can have we can squeeze the fluctuations of vacuum and then displace them. Now, the question of this line of research is whether we can generate light that combines both properties, the spectral purity of lasers and the quantum fluctuation properties of squeeze states. And let me go deeper on this problematic by analyzing how laser light and how squeeze states are produced, because they are very similar in a way. In lasing, you have basically a driven dissipative phase transition. Okay, so you have some critical parameter, and below the critical point, you are like in an off phase, in which you have no photons in your cavity. You have vacuum, and as you increase your critical parameter, that could be some type of pumping, you enter in the lasing phase, which is powered by a stimulated emission. Okay, and you develop a coherent state. And the deeper you go into this lasing phase, the narrower your spectrum is, the narrower your line is. Now, how do we produce a squeeze vacuum? Turns out that you also produce it in systems that have a very similar phase transition, okay, like an optical parametric oscillator. You have an off phase in which the cavity is basically in vacuum, but now as you approach the critical point, your state starts being squeezed in phase space, but then you have also an on phase with stimulated emission, in which this squeeze state splits into a mixture of two coherent states. So you see here there is a very critical difference, because for lasing I wanted to use stimulated emission and be above the critical point, but to produce a squeeze light I need to be below critical point and avoid stimulated emission. So it's kind of tricky to have both things at the same time. Okay, so what I would like is to obtain a stimulated emission and squeezing. And formally, what would this be? To do that, I want to recall that the normal basis to describe a harmonic oscillator is the number basis, which for a cavity is just the Fock states that tell you how many photons, states with a well-defined number of photons. Okay. But you need to know that squeezing is generated by a unitary transformation, a squeezing operator. So I can define a new basis applying that unitary operator, which is a basis of squeezed number states. So by having lasing and squeezing, formally what I mean is that I would like to take the Poissonian distribution corresponding to lasing in the normal photon number basis, but have that in the squeeze basis, okay, due to stimulated emission. So this is what I try to do. Actually, there was earlier proposals in superconducting circuits done by members of my group, like Diego, Juanjo, and I wanted to do this in the optical regime. So we proposed a system consisting of a cavity with some gain medium and a nonlinear crystal. And basically, we showed that this nonlinear crystal that implements a 2-photon driving into the cavity, you can tune the intensity and the frequency of this drive to enter in a regime in which it's those squeezed states that I showed you, the ones that coupled to the gain medium. So you obtain lacing, which is this ring, this mixture of coherent states with all possible phases, into these squeezed bases, which brings you into this weird shape when you go back to the original photon number basis. So this was the result. We saw that in this type of system, you still have this line narrowing that defines the monochromacity of a laser. But you also keep some quantum properties. And we saw this, for instance, with a metrological example. We feed this into a Michelson interferometer. We plot basically the sensitivity of this state. Sorry. And basically, we saw that it's larger than the standard quantum limit, meaning that there is some quantum property there that is giving you an extra sensitivity. Okay, so it's a proof that this state is not just a standard laser, which is a classical state, but there's something quantum in it. So what's next? This is still an active line of research. I wanted to take advantage of this talk also to welcome Rodrigo Grande, who's just started the PhD working on this topic with me, and he's sitting back there. We want to implement this in different systems, maybe with less experimental overhead. And what we have in mind is using trapped atoms and cavity-assisted Raman process to engineer this type of coupling into squeeze states and do this laser. There are many follow-ups to this idea in atoms. And another thing we want to investigate is to use this squeeze laser to drive matter and see how we can transfer these quantum correlations and how we can exploit this to do quantum metrology. Okay. I found this flyer, which I like very much the 90s look of it, because I was looking for this quote of the laser is a solution looking for a problem. This was like a critic done by, well, not a critic, it's a comment done by the actual person that built the first laser. And now I feel kind of the same. I feel the same with this squeeze laser, right? So I think right now maybe it's a solution looking for a problem, and that's what I'll try to figure it out, right? Okay, with this I move to the second line of research, which is implementing quantum optics in the terahertz. As you all know, the terahertz is this range of the electromagnetic field between the microwave and the infrared and visible. And this range of frequencies have a series of very interesting properties. It has good transmittivity through medium that are opaque in the optical, for instance. It interacts with rotational transitions in molecules. It has small atmospheric attenuation, which is related to the first point. It's safe, it's non-ionizing, and it provides high bandwidth. So this makes it a very interesting range from a technological perspective. For instance, it gives us prospects to do quantum control and sensing of a variety of molecules, maybe wireless quantum secured communication. As I said, it's interesting for security. It's been used for medical imaging. So there are many applications. But let's talk about exploiting this for quantum technologies. And something interesting is to think about compare what a qubit in the terahertz would be with a qubit, for instance, in the microwave. So a superconducting circuit qubit, such as a Trasmon, has a transition frequency of a few gigahertz. And that means that has an associated temperature of 0.3 Kelvin. That means that we need to place these systems in dilution refrigerators to go to a millikelvin regime so that they are not thermally excited. And that is a serious challenge in terms of scalability. A terahertz qubit with a transition of 1 terahertz would have an associated temperature of 48 Kelvin. That means we could use helium cryostat, which is much simpler and scalable to operate with this qubit. And having a qubit like this would be a requisite to start implementing quantum technologies in the terahertz realm. But there is the challenge that there are not naturally occurring qubits which have transitions in the terahertz and that couple efficiently to the terahertz electromagnetic field, which is basically the requisite we need to be able to control these qubits and do any type of quantum technology. So this is the type of challenge that I'm addressing in this line of research. And we are working with an idea that we didn't have. It's something people have been talking about for years, which is using not a terahertz qubit, but an optical qubit to couple to terahertz light. And the key point is that this qubit with an optical transition, the states that compose it should have a permanent dipole moment. And I took this as an example. It's not a real example. I just copy orbitals from a paper. But you can see that, for instance, we could have this state which has no dipole moment because it's symmetric. But this other state has an asymmetric charge distribution. So it has a permanent dipole moment. Okay? So we would like something like this. And then the trick is that you drive this qubit resonantly with a laser. Okay? So we all know from undergrad quantum mechanics that if you excite resonantly a transition and you start, for instance, from the ground state, you will have what we call Rabi oscillations. We will have oscillations between the ground and excited state. And the frequency of these Rabi oscillations, the Rabi frequency, is given by the dipole moment and by the amplitude of the electric field driving the system. So in principle, we could tune this electric field to tune this Rabi frequency into the terahertz regime. But now, since we have a permanent dipole moment, this would mean oscillations in the dipole moment that are occurring in the terahertz range. And this will give rise to radiation in the terahertz by driving an optical qubit. So this was a bit a hand-wavy explanation for the quantum opticians in the room. We can think of it in terms of the dress states of the qubit and the laser light that form these doublets of energy levels. And what is happening is that the energy transition within a doublet, which has the Rabi frequency of the terahertz, is now normally dipole forbidden, this transition, but by having the permanent dipole moment, one can check that it becomes allowed, and we have this transition. I just said the same thing with a completely different language. As I said, this line of research wants to exploit this idea and focus on the generation of quantum light. People has exploited this idea, for instance, to do terahertz lasing. And in this work, we focus more on the regime of generating single photons, which is a crucial step to implement quantum tech in the terahertz. So we are combining this idea of driving this polar quantum emitter with the design of specific cavities in the terahertz that will enhance this emission process, right? This was done at Universidad Autónoma de Madrid just before joining this institute. And well, we obtained this type of results. I won't enter very much into the details, but one nice property is that we can tune the intensity of the emission and the frequency of the emission just by changing the Rabi frequency, which, remember, Rabi frequency is the amplitude of the electric field you use to excite. So you can tune these properties optically. And you can also look at the quantum fluctuation properties of this radiation, which is what I saw in this plot. Again, I don't enter in the details, but you see changing colors. That means that I can also optically tune the quantum statistics of this light in the terahertz. So we are kind of showing that we have optical control to develop a bit of a toolbox to generate light in the terahertz with different properties. This is more of the same, just to show. You don't need to understand what I'm showing here, but you can appreciate that this is frequency correlation map, so coincidences between photons. And you see that it's really rich. No? There are many patterns of coincidences of process that are going on. So it's, without going into the details, you can see that it's really a complex system in which we are generating a rich phenomenology. So what's next? We want to exploit these ideas to generate entanglement, steady-state entanglement between qubits mediated by terahertz structures. We are also thinking about the possibility of stabilizing cut states in these terahertz cavities, which could be used for continuous variable quantum computing, and also study how we can coherently couple these terahertz and optical photons for many applications like upconversion detection, etc. I also want to mention and welcome another PhD student, Yanis Lefour, who is going to start very soon and is back there clapping, and also my UAM collaborators that which we are closely related in this line of research, particularly Diego Martín Cano, who is an expert in molecular automechanics. Okay, I don't know if I'm going too fast or too slow, but that takes me to the last part of the talk on the topic of detection and analysis of quantum correlations. And here I do machine learning for quantum parameter estimation. The idea here is that we have some system that will act as a sensor, for instance, to sense the electromagnetic field around it. And this is operating in a driven dissipative way, in which it is emitting continuously excitations into an environment. And we are detecting these excitations and monitoring them. Okay? So the task is to use this information to infer this unknown parameter in the environment of the detector, like for instance the frequency of an electric field or the amplitude. So this has relevance for many applications, metrology of time-varying signals, magnetometry, spectroscopy. There are really many applications, as I saw at the beginning, that fall into this framework. And one particular motivation that I like very much is the one I said before about imaging and fluorescent microscopy. Because here, contrary, for instance, to quantum computing, I think that experiment is way ahead theory. They are able to make experiments that are really difficult to reproduce and to exploit from a theoretical point of view. Because thinking of these so many emitters producing such a massively multiplexed signal with quantum correlations, it's really difficult to theoretically extract all the information that there is there to extract. So that's kind of the challenge I want to tackle, and I wanted to assess what is the potential of machine learning tools to boost all this process. So I studied this starting with the simplest system I could think of. This is just a qubit. As I told you, the qubit is embedded in an environment, is driven by an external field with some detuning and inducing some radio frequency, which are the parameters I would like to estimate. And the system is continually emitting single individual photons because it's a qubit, so it can only emit photons one by one. We detect this signal continuously, and we get clicks anytime that we detect a single photon emitted by this system. So the formal correct approach to infer an unknown parameter to estimate this theta from that data is to use Bayes' theorem. So Bayes' theorem tells us what's the probability of the parameter given the data, and that's given by the probability of the data given the parameter divided by the probability of the data times your prior knowledge about the parameter. So we can in principle just apply this and obtain, for instance, this type of probability distributions in which you see that in time it gives you kind of a Gaussian center around the real value here. So why not just applying this recipe? What you need here is to compute this part, the likelihood of the data, which is something we can do with our theory of open quantum systems. The problem is that this will require an extremely good modeling of the system. So if you have any source of noise, imperfection, you need to theoretically control that very well and put it into your model. And it's really computationally expensive, because if you remember, you can compute this likelihood, but you have the probability of the data in the denominator, and that's basically the integral of this likelihood over all the parameter combinations. So if you have many parameters that you want to infer, this becomes really computationally expensive. So this is the Bayesian way, is the formal, perfect way of addressing this problem, but it's very challenging. And our proposal was to use deep learning architectures, feed them the data. In this case, the data are the time differences between the clicks in the detector, and then just train it to give directly the estimation of the parameters. So we did this. Let me show you quickly just one result. So here I'm benchmarking the results that I will show the neural network with the error in the estimation made by the Bayesian method. Here I am estimating the frequency of the external field as a function of the frequency itself. And for this benchmark, something interesting is that we computed the error. This yellow line is the error using all the data, the single photon detection events, and this other line is assuming that we have an imperfect detector and we are not able to resolve the intensity at the single photon level. So we can measure the intensity, but I cannot tell the exact point where a single photon was detected. That means I have intensity information, but I don't have these quantum correlations that are encoded in the individual photo detection times. And this difference is telling you something interesting, which is that there is information to be gained by looking at the quantum correlations. Okay. Now, what happens when instead of doing this Bayesian thing, I just train a neural network? We trained two types of neural networks: a recurrent neural network giving this result, and then a dense neural network with some pre-processing, which, as you see, gives, I don't know if you saw, but it's basically overlapping with the Bayesian result. Okay, so we can achieve the same performance as Bayesian inference. We can take this to multi-parameter estimation, so now estimating the frequency and the amplitude of the field at the same time. And you see that the error landscape made by Bayes' theorem, this structure is basically physical, it's ingrained in the dynamics of the system, is completely reproduced almost one by one by the neural network. The difference is that each pixel in this 2D plot was done with 100,000 simulations of individual rounds of the experiment, and each of these shots, obtaining the estimated parameter doing Bayesian inference took 10 seconds using state-of-the-art sampling methods. But it took 4 milliseconds using the neural network. So there is a massive computational advantage here. We can also take these models and compress them very much with this utility called TensorFlow Lite, and turn it into a very light model that you can plug into a microcontroller, with the idea of being able to do this inference on the edge, like in the actual experimental setup, without needing to go into your laptop and do the thing. So what's next in this line of research? Right now, this proposal of using machine learning is directly spitting a single point estimate. So it's telling you what was the estimate it has of the parameter, but it doesn't tell you anything about the possible uncertainty in this estimation that would be encoded in this Bayesian probability distribution. So the next steps for us is to use probabilistic machine learning models like normalizing flows to really obtain all the probability distribution of the parameters. And then we want to go way beyond this very simple model of a single qubit into something more complex, like a quantum imaging setup, in which I have tens of fluorophores, and instead of a single photon counting signal, I may have thousands of photon counting signals, and I want to correlate all of them. It is really a massive, there is massive room to increase the complexity and really apply this in situations in which it's not viable to use Bayesian inference. Okay, so that brings me to the end of the talk. I hope I gave you a bit of a flavor of the type of research I'm interested about. Just to wrap up, I told you that we can design sources of light that combine the coherence of lasers and the quantum correlations of squeeze states. I have told you how we are developing quantum platforms in the terahertz range, exploiting optical polar quantum emitters. And finally, how deep learning can boost applications in quantum parameter estimation. I would like to acknowledge and celebrate that all these lines of research are being funded by Proyecto de Generación de Conocimiento. And thank you all for your attention.
Well, thank you, Carlos. Very, very nice talk. So, questions? Yeah.
Okay, I have at least 4 questions. Wow. First, probably I missed something. Which is the order of parameter order, sorry, of in the phase transition?
Yes.
Yeah,
I didn't put it because I didn't want to go into those
okay,
details.
Because I think this is important.
Yes, for the lacing,
Yeah.
it's it depends very much on the actual model, the implementation of the laser. But it could be, for instance, a cooperativity, like the is 4 times the coupling between the gain median and the cavity divided by the losses and the pump. I don't know, it's a very
So you have
complex.
to build this.
It's very model specific, and there are many models. That's why I didn't want to enter into the actual thing and then having to explain for this particular model, blah, blah, blah. It depends on the model, okay? But it can be related to the pumping, for instance.
Yeah. I am not familiar with the Fisher information, but I suppose could be quite related to the Shannon information, or related to the entropy.
Yes.
Can you remember me which is the difference between Shannon and Fisher?
No, I mean, maybe Alejandro Rivas over there, who I don't know are you here, Alejandro? No, I don't. No, honestly, I don't know. I can tell you. I can tell you that Fisher information is in the end is measuring a distance between the probability distribution and the probability distribution if you wiggle the parameter a little bit. Okay.
No, because I will tell you this because in a certain sense this is related to what is called the H theorem. The H theorem. So you don't know anything about this, no? Okay. Okay. The second question is, are you aware that TeraS is also good for plasmonics?
Yeah.
Plasmonics.
Yeah. Good for what, sorry?
The TeraS frequency. Okay. It's very important also for plasmonics. Are you working, or you are thinking to work on plasmonics in this regime?
So. I said that I have collaborators at Universidad Autónoma. Yeah. And for instance, there is a very strong group on plasmonics there. Okay. And for instance, the cavity that you showed is that were like 2 spheres. That was a plasmonic cavity to operate in the terahertz. Okay. Yes. So they are more into the nanophotonics.
Nanophotonics. Okay.
You know. So yes, plasmonics are involved in business. It's not what I am personally doing.
You're not personally. And the last question is, I am really very surprised when you write the Bayesian probability, no? And you put open quantum systems. But in fact, you are not working on open quantum systems in the following sense. You are using neural networks, and if I understood well, due to the fact it's very difficult or expensive to work on the stochastic processes in order to get this probability, you prefer to use neural networks. This is the message you want to transmit us?
The difficulty doesn't...
Because, let me finish. Open quantum systems is very well known. You can work on Lindblad, you can work on even path integral and so on, okay? It takes time, obviously, but it's not so difficult. I don't know, probably with neural networks you wrote 4 milliseconds, and for the other was 10 seconds or something like that. So what you are telling me is much better to use neural networks than the open quantum system theory?
Again, it's not that neural network is replacing open quantum system theory, and the difficulty here, the challenge, is not so much because it is an open quantum system, but it's more related to when you want to do multi-parameter estimation, and you have many parameters, so your landscape is really big. It's a general problem. Also in astrophysics, any problem that you have to estimate many things at the same time. The challenge was not to do the open quantum system also, the master equation, all this, focuses on what's the dynamics on the system removing the environment. But here what I'm focused is on the records I get from the actual environment. And this can also become like a very long chain of data and many chains of data if I'm
Okay.
not listening.
Nice.
So also a little nuance.
Okay. Okay, thank you.
Okay, yes, so
In one of your slides, you say that the atmospheric attenuation is small for terahertz radiation. What do you mean? For small laboratory paths, or because for us, for astronomers, the atmosphere terahertz frequency is totally opaque.
I see.
That's why we have to go very high to
Okay, yeah,
that's to observe.
that's interesting. I honestly, I'm not an expert on that part. These are claims taken from the use
Exactly
of
at 1 terahertz, the transmission of the atmosphere, the whole atmosphere is zero.
I see. Okay. I think it's more like in conditions of fog and dust, because you are collecting things that come from space into cross the atmosphere into your detectors, right? I think this is more thinking about
The main
wireless
problem
communication and
the main problem is water lines.
yeah.
Water vapor in the atmosphere absorbs.
Yeah,
everything.
I'm really scared to get into a discussion on that because I know nothing about it. To be honest, these are claims in papers on terrestrial technology. This is one of the things they say, like, look,
Maybe they
look at
refer to a small paths in
They-
the laboratory.
in the laboratory.
Yeah.
They
few
refer,
meters or
they speak of,
something.
look, they say that 6G, they want to push it into close to the terahertz, right? So this is not a small path laboratory. This is for wireless communication, right?
Yeah.
And I remember they spoke of fog, dust, all these type of things. Signals in the terahertz can be better than the optical. I know this is such a complicated topic that I may be missing many things, no? And also there are particular resonances. I honestly don't know, but it's an interesting point. I would like to know more about that.
It is not to detect weak signals from the sky, it's just to propagate signals. If they
Weak
Yeah.
or strong. If the transmission is zero, it's zero.
But also the type of atmospheric layers that we have to cross is different, no? In wireless communication and things that come from the universe, no? I guess.
Nitrogen and oxygen.
yeah, Beatriz.
Yes, nitrogen and oxygen is good.
Sí, sí.
Yeah.
I have a question. Well, more or less in the very beginning, you explained the difference between classical light, you put coherent light, laser, and the quantum light, you say,
Mhm.
well, superposition, no?
Mhm.
And now I'm thinking of the speckle of laser beams. You know, the speckle is the interference with themselves.
Mhm.
Now, how you see this from the point of view now of the quantum light?
I think you are invoking a degree of freedom, which is like the mode profile that I was not invoking here. Right? So this was more about the internal photon number fluctuations, right? And I don't know much about speckles, but I guess that has to do with modifying the mode profile of your laser. I don't think that enters into. It's a degree of freedom I'm ignoring there. Right? And I don't think it has to do. I don't think that would turn the laser into anything quantum. It would still, you know, if you put detectors on that and you split that speckle and put two detectors and you get a click in this detector, that won't tell you much about the click in the other detector unless you are resolving spatially this mode structure, blah blah. But that's because of the mode profile, right? Not because of the internal degree of freedom of the photon number distribution. I don't know if I was clear, but I'm not so much. It's a bit nuanced.
Yeah.
Thanks for the talk. It was very interesting. I wanted to ask about this laser. What's the intensity? Is it comparable to normal lasers, or did you explore it?
Yes, it's comparable, but also the intensity distribution is not like unimodal. It's not like a Poissonian distribution. Okay? You see, it has a weird profile in phase space. If you look at photon number, It has like a narrow peak and then a broad, a broad tail. So it's not something you can describe well with a single number like the intensity. It has weird fluctuation properties.
Then, for a very more precise question, the expectation value of the E field is more or less the same as a normal laser. So display alpha, let's say the radius,
it is zero because it's okay. We are entering too many details, but you know
the radio of this donut, the radius of this donut.
the radio changes. It's not constant.
I know, but in the squeeze basis.
It's like a normal laser in the square basis.
Okay, so.
Very silly question. So for you astronomers, what we detect is 100% classic light, no? We don't detect quantum light, no?
I think so, but I might be wrong. Do you do quantum optics experiments?
No, we put our telescopes and we wait.
I mean, quantum optics was born from radio astronomy, okay, from the Hamburg-Brown interferometer, in which they thought, oh, let's correlate the intensities from two radio telescopes, and there is some interference, and we get information, and this challenge very misconception. But in the end, it was classical light what they were detecting. Maybe there are extreme astronomical events in which you generate squeeze light or something like that. I don't know. I'm not astronomer.
So what you call the terahertz for us is what we call the far infrared. That is cuando we put the telescopes in space normally. So what's your theory and methods to produce terahertz light? Can you use it to detect terahertz light?
One idea I mentioned in the outlook, we are studying the coupling of terahertz light to optical photons. And one idea there is that you can upconvert light that is coming into optical light because we have very good detectors for optical photons, right? So that's one path towards that that direction. I don't know if it's the best path, but it's something we can explore there. Thank you.
Okay, is there any more question? If not, let's thanks all the speakers of today. They take a lot of time to prepare this talk, so thank you to all of them. And well, now, to conclude this event, we have the pleasure to announce the formation of the igualdad, I don't know how to traduce it, equality in English, I'm not going to say, but yeah, so please. I think it's this one, no? Ah, ya.
Hay un vídeo de...
Ah, vale. Bueno, te dejo...
¿Tú tenías
Te dejo
abierto saco?
No. Está metido con el informático.
Pero no lo grabamos, ¿no?
Voy a cortar si quieres.
Yo creo que no
Que no
grabamos.
está, pero si no lo edito luego y...
Empieza ella.
Pero él, bueno, le preguntamos. Bueno, Marta. Albert, ¿viene alguien más junto contigo? ¿Janem, inglés o español o castellano?
Yo creo que es mejor
¿Te
inglés,
digo?
¿no?
¿Inglés bien? Sí.
Que como ahí... Espera, voy a cortar.
Pues son muchos, ¿eh?
No, y los que faltamos, sí, todavía.
No, pero espérate más porque falta gente aquí, ¿no?
No está Miguel, no lo veo.
Luca no puede venir, ¿eh?
Luca,
Falta
Miguel,
Judith, que no estaba,
Judith
no estamos
y Carmen tampoco.
Hay que ponerle
O sea
con
que-
Photoshop.
Sí.